All right, good afternoon, everybody. So today we'll discuss areas in polar coordinates because I just realized that we only have, I think, 3 lab meetings left. So we need to pick up the pace. And I thought of merging our discussion of sections 10.2 and 10.3 because they are basically intertwined with each other because section 10.2 talks about graphs in polar coordinates, including solving for points of intersection and so on, while section 10.3 talks about setting up or computing integrals that will give the area of regions bounded by polar curves. So I guess it would be nice, or it would be more efficient to talk about setting up the area of of regions bounded by polar curves in conjunction with sketching the graphs of polar curves, because that will allow us to speed up the um, the um, the discussion without giving up any of the rigor or the details there, right? Because I will show you how to sketch the graph of certain um, polar curves in detail so that we will have a nice idea of how to set up the integrals that will give us the area of those regions, all right? Now, and I think section 10.4 will be the end of Calculus 2 for you guys because due to class suspensions, the lecturers, I think, decided not to cover section 10.5. Let me double check that so that I won't give you false info. Yeah, section 10.4 would be the last section for Cal 2. So we will not cover 10.5 here, right? So let's see. All right, let's first have a quick recap of what are the usual graphs that you see in polar coordinates. Well, one way you can do is transform a polar equation into its Cartesian equivalent, right? So you do the conversion factors we talked about last time, and then identify the graph using the Cartesian equation. Because it doesn't matter if you look at the polar equation or a rectangular equation, their graphs will look identical in the two-dimensional space. So yeah, but I guess you have seen that converting from polar to Cartesian will require more work. Even if you are able to transform all your r's and thetas into x's and y's, you will still need to do some algebraic manipulation in order to see the exact form of the equation and relate it to graphs or conic sections that you have seen in pre-cal, right? So, but we will just deal with some basic polar curves. So perhaps I will list down, I'll try to list all of them down. Hopefully I won't forget anything. I guess we have the basic graph. So let's see, polar curves, right? So we'll have the basic curves or the basic graphs. Let's start with theta equals k. Theta is a constant. Sorry, theta equals a constant. So this is a ray starting at the pole, right? And then you have r equals theta, which is your Archimedean spiral. Okay. And then we'll also deal with circles. And circles can take several forms, but the more basic ones are the following. R equals A. This is a circle centered at the pole of radius A, or radius absolute value of A. We'll have R equals A sine theta, which is a circle tangent at the pole lying on the y-axis with diameter A. And then you can also have R equals A cosine theta, which is similar to R equals A sine theta. Oops, I don't want to copy that. So this is tangent at the pole lying on the x-axis with diameter A. right? Now, I think I mentioned to you last time that if you have a sine, um, that probably will be dominantly on the y-axis because sine is related to the y variable. And cosine, if you have graphs involving a cosine alone, so it will predominantly be on the x-axis because the x variable is related to the cosine, if you remember the conversion factors, right, or the conversion equations. Now, aside from circles, we will also talk about limaçons. And they come in the following form. You have r equals a plus or minus b sine theta. So this is a limaçon that will mostly lie on the y-axis. And you have r equals a plus or minus b cosine theta, a limaçon, which will lie predominantly on the x-axis. And this will have four forms depending on the ratio a over b. If a over b is less than 1, then we have a limaçon with a loop. If a over b is equal to 1, we'll have a cardioid or a heart-shaped graph. If a over b is between 1 and 2, so we have a dimpled limaçon. Or others call it a limaçon with a dent. And lastly, if a over b is greater than 2, then we will have a convex limaçon. Okay. Now, how does this four look like, or how do these four plots look like? So, okay, all right. So you can imagine the ratio a over b being inversely proportional to the amount of force you will use to poke a circle. So you start with a circle. If a over b is little, that means you will poke the circle extremely hard, all right, to the point that it will create a loop. That this will force some portion of the circle to go inside out, forcing you to have a loop. If a over b is greater than is equal to 1, then you will use a little less force, just enough to put a heart-shaped juncture here. So you'll have a cardioid or a heart-shaped graph. If a over b is larger, so it's between 1 and 2, you'll poke it a little more to get a dimpled limaçon like this, or a limaçon with a dent. So you have the dent over here. So that's the dent or the dimple. And if a over b is greater than 2, then you will just poke it with little force that will barely make a dent into your circle. So this is a convex limaçon. All right. So these are the four types of limaçons, and it's important that you can identify what kind of limaçon do you have, because for plotting limaçons, I'll suggest just use 4 values or 5 values for theta, and just rely on knowing how the graph should look like in order to draw the final picture. So don't worry, in one of the examples later today, I'm going to show you how to sketch the graph of a limaçon and before getting the area of regions involving limaçons. All right. Then aside from limaçons, okay, let me just put that here. We also have what we call lemniscates or propellers. All right. So other books call it a propeller. The equation is r squared equals a sine 2 theta. Or r squared equals a cosine 2 theta. So the graphs will look like this. A sine 2 theta will look like this. And a cosine 2 theta will look like this. That's why I prefer to call them propellers, because they really look like propellers. And it's easy to spot lemniscates because it's the only basic polar curve that we will deal with that has an r squared on the equation. Or you can generally see them as r equals the square root of a sine 2 theta. So they are easily spotted. And I think lastly, we'll have roses. But I guess the book calls them petals, but I prefer to call them roses. So whenever I say roses, I refer to petals, right? So their equations are of the form r equals a sine n theta and r equals a cosine n theta, which is different from lemniscates because lemniscates have a 2 theta inside the angle. It is strictly a 2 theta. Unlike for roses or petals, wherein the value of n can be any integer, right? And then the left-hand side of roses has an r, but lemniscates do have an r squared, right? So here the value of n is an integer, determines how many petals or how many leaves your rose will have. So if n is odd, you will have n petals. If n is even, you will have 2n petals. And I'll elaborate more on roses later when we deal with examples for areas involving roses. Okay, so that's a quick review of the polar graphs that you have seen in section 10.3. The details will be embedded as we discuss some examples from section 10.3. So, oh, by the way, this is worksheet 22 in my website where I copied the exercises from section 10.3 for you guys to practice on. But I'll try not to use these examples. I'll leave all of this to you as practice. And let's look at some examples that I prepared here. So here, sketch the region described in each of the problems. Then set up the integral that will give its area. All right. Now, one thing about this is we need to recall the formula for the area. So the area in polar coordinates will look like either a equals 1/2 integral from alpha to beta of r squared theta d theta. All right. So don't forget there is a mainstay 1/2 here, which is from the area of a sector of a circle. The upper and the lower limits of the integrals are angular components because we're integrating with respect to theta. So lower and upper limits should be angles in radians, right? And then the integrand is the radius squared. All right. So these are the different components. And this is used whenever you only have one curve involved. But if you have two curves involved, you will have 1/2 integral from alpha to beta, then outer radius squared minus inner radius squared theta. So I will illustrate later how to find the outer radius and the inner radius so that you can complete your formula. Okay, so let's see some examples, and hopefully by then you will interact with me if you have some questions. So let's do an easy one first. Say the region bounded by r equals secant theta and the rays theta equals pi over let's see, pi over 6 and pi over 3, and theta equals pi over 3. All right. Again, the first instruction is to sketch the region, but even if you're not required to sketch the region, it will be helpful to have an idea of how the region looks like so you can identify what is the required radii that will go inside the integral. So here, let's start with r secant theta, right? Oops, let me see, solution. Do you guys know the graph of r equals secant theta? I know it's not in the list that I presented earlier. So whenever you forgot or it's not a common polar graph, so what you can do is to convert it into its Cartesian form so that you can identify how the graph will look like. Because again, the graphs of a polar equation and its equivalent Cartesian equation will be identical in the two-dimensional space, right? So here I can say, oh, I can first say that this is r equals 1 over sine theta. Oh, sorry, not sine, cosine theta, right? And then multiply both sides by cosine theta. I'll get r cosine theta equals 1. And I hope you remember that r cosine theta is just equal to x. So we'll have the vertical line x equals 1. So let me draw here. Some axis. There you go. Okay. Now, so the graph is r equals 1. So that will go here. So this is the graph of r equals secant theta. And then we have the two rays. Theta equals pi over 6. So that's easy. So that will just be here. Okay. So this is theta equals pi over 6. Assuming that this is pi over 6 units. All right. That's how I found that line. And then the other one is theta equals pi over 3. Theta equals pi over 3 could be somewhere like this. So this is theta equals pi over 3, assuming that this is pi over 3 units. All right. And so our shaded region will be this triangular portion here. All right. That's my shaded region. Okay. Now the area, again, I'm doing it in polar coordinates. So I have the mainstay 1/2 integral of, we are integrating with respect to theta. So I know that the bounds should be angular components, right? But if you look at the region, what is the starting angle and what's the ending angle? So the region started here, right? Which is at theta equals pi over 6. It will go all the way until pi over 3, right? So you will think of here as you have a radius and you will scan that radius as you go along the unit circle, right? But it will not take a full revolution for that line segment or for that ray, because that ray that will go through the region will just start here, and then it will go past here until there. But right after pi over 3, there's no region left, right? So there's no shade. There's no shaded portion anywhere else after pi over 3, right? So that's how I knew that the lower bound would be pi over 6 and the upper bound would be pi over 3, right? And then how to know the integrand? What I do is to draw a ray here, and imagine this ray scanning the entire shaded region. So I will think of it as say a hand of the clock that will travel along the region. So I know that here the outer radius will be this, right? That's the ending value, and there is no inner radius because it will always start at the pole and will end up at the black line, right? The vertical line. If my dotted line is here, right? Then it will still start at the pole and will end up at the vertical line. And you will see that all throughout theta equals pi over 6 until pi over 3, my dotted line will start at the pole and will end at the vertical line. So that means the radius here is the equation of the vertical line, right? And so my integrand would be secant theta. But remember, in polar coordinates, the integrand is always squared. All right. And so this will be the integral that will give you the area of the shaded region. Though not required, we can also go ahead and evaluate this integral because it's not that hard, right? So secant squared theta has integral tangent theta. So 1/2 Integral of secant squared is simply tangent theta, evaluated from pi over 6 until pi over 3. So this guy would be 1/2 tangent of pi over 3 minus tangent of pi over 6. So this would be 1/2. And then you need to go back to your unit circles. What is tangent of pi over 3? Tangent of pi over 3 is root 3. Minus tangent of pi over 6, which is 1 over root 3. Hopefully I did the calculations right. So just let me know if that's correct. And then we can simplify. So this would be 1/2. It's going to be 3 minus 1 over root 3. So this would be 1/2 times 2 over root 3. That's going to be 1 over root 3 or root 3 over 3. All right. So the area of that shaded region is root 3 over 3. Now, imagine setting up the area using Cartesian coordinates. You will integrate top minus bottom, right? But that's fine, but that's different. In rectangular, you do top minus bottom. So in polar, you look at the outer radius and what's the inner radius. If the inner radius turns out to be the pole, then you will have a single term in the integrand because the pole has equation r equals 0. Okay, is that clear, guys? I hope that made sense. It's an easy one because I want you to see the process, okay? So let's look at another one, which is a usual problem I see in exams or quizzes. Find the area inside the inner loop. So region inside the inner loop of r equals 1 minus 2 cosine theta, right? So note the graph is a limaçon, right? If you look at this is of the form r equals a minus b cosine theta, so it will be limaçon. In particular, a over b is equal to 1/2 less than 1, so we have a limaçon with a loop, right? Now keep that in mind, but to get a nice idea of a nice idea how the graph will look like or how the limaçon with the loop look like, we can make a table of values for certain values of theta r. Okay. Now for limaçons, it is helpful to get the r values for the quadrantal angles. So we'll not use a lot of points here. I think 5 points is enough, or 4 points are enough, as long as you know the shape of the limaçon, right? I know I have a limaçon with a loop, so I can leave with only 4 function values or 4 points on the graph. So I'll use the quadrantal angles for theta. So I can choose theta equals 0, pi over 2, pi, 3 pi over 2. Then I usually throw 2 pi as well here. But I know that the value here is the same as the value here, just to have a close for the entire region, right? Though theta will take any angle between 0 and 2 pi, but of course that's physically impossible to find all their r values. But knowing this, the values at this 5 theta values will be enough because we already know that we are expecting a limaçon with a loop, right? So let's plug in 0. When theta is 0, cosine 0 is 1, 1 minus 2, so that's going to be a negative 1. When theta is pi over 2, this will be 0, 1 minus 0, so we get 1. When theta is pi, so this guy is negative 1 times minus 2, so that's plus 2, 1 plus 2, so we get a 3. When theta is 3 pi over 2, this guy is 0, so we get a 1. And at 2 pi, I'll just repeat the value I got for 0. All right? And then let's sketch the graph. Okay. Now, what are the R values that we have? We only have two R values for the quadrantal angles. We have 1 and 3. Of course, we have -1, but that's similar to 1. So I'll need the two concentric circles just to help to guide me in drawing the R values. So let me draw, say this is R equals 1, and this is R equals 3. All right. So this will just help me plot the R values, right? Okay, starting off with with theta equals 0. Theta equals 0 ray is here, right? That's theta equals 0. But we need to plug in R to plot R equals -1. So since R is negative, we don't plot in the original direction, but we go in the opposite direction. So instead of 1 unit here, I'll plot 1 unit in the opposite direction. So that means our first point will be here. Okay. When theta is pi over 2, this is our direction. R is equal to +1, so I'll plot the point in the pi over 2 direction, 1 unit away from the pole. All right. When theta is pi, so we are in this direction, R is equal to 3. So here's the radius 3 circle, so my point will be there. When R is 3 pi over 2, we're here. R is +1, so we'll get a point there. And when R is equal to 2 pi, we'll be back at -1. All right. So if you will plot this, I'm expecting a limaçon with a loop, so it will look like this. Let me just cheat a bit here and enhance the figure. Okay, so how was it plotted? Let's look closely, right? We started theta equals 0. We knew that we have this first point. If you plug in theta values, so you will get an R value that is negative. You'll be here, okay? And then you will hit the pole again. But after hitting the pole, you'll go here. This is my second plotted point. Third point, fourth point, and then I will re-enter the loop at some point, and then it will be closed at theta equals 2 pi, right? That's how we got the limaçon with the loop, right? We are interested in finding the area inside the inner loop, so we look at this shaded region, all right? Now, what are the theta values that are spanned? What are the theta values that are spanned by the shaded region? Remember, you start at theta equals 0. We are here. Theta increases. And then at some point, we will hit the pole, right? But after we hit the pole, we will be outside the inner loop. So we will be on the larger loop still at 3 pi over 2. We're still at the larger loop. But after 3 pi over 2, at some point, we will hit the pole again, and we will re-enter the inner loop again. So the lesson here is that we enter and exit the inner loop when we hit the pole. And the pole is when R is equal to 0, right? So basically, we can solve when R is equal to 0 because that will tell us when does the loop start and when it will end. So note, we enter and exit the loop, the inner loop, at the pole, right? And the pole is the point when R is equal to 0. So I want to know what's the angle or what's the theta value when we are at the pole. So the pole is at R equals 0. Our limaçon has equation 1 minus 2 cosine theta. So I'll have 1 minus 2 cosine theta equals 0. So we'll have 1 equals 2 cosine theta. Then cosine theta is equal to 1/2. So what's the value of theta then? When is cosine equal to 1/2? Cosine is 1/2 at pi over 3. and the other one would be at 5 pi over 3. Okay, so that means we will be at the pole when theta equals pi over 3 and 5 pi over 3. So if we zoom in into our limaçon, right, there we go, right? Remember, we start at theta equals 0. When theta is 0, we are at -1, right? And then you give larger values of theta, you'll be here. But the theta equals pi over 3, we will be at the pole. So that means we have covered half of the inner loop. Unfortunately, my cardioid, my limaçon here is not properly drawn, but expect that it is symmetric with respect to the horizontal axis, right? So what I'm trying to say is that this area is equal to this area, supposedly, if I have a perfect sketch of the limaçon, right? So that gives me an idea. Instead of integrating over all theta values, I can just integrate from 0 until pi over 3, because at that point I have covered half of the loop, right? And I'll just multiply my answer by 2 in order to get the area of the entire inner loop, right? So let's just keep that in mind. But again, the point here is we started theta equals 0, then increase theta until we hit theta equals pi over 3. We know exactly when we will hit the pole. And at theta equals pi over 3, we will be exiting the inner loop. So theta equals pi over 3, increase theta, that's pi over 2, theta equals pi, theta equals 3 pi over 2, we're here. But the theta equals 5 pi over 3, we will be re-entering the loop again. So we can again integrate from 5 pi over 3 until the closing of the loop at theta equals 2 pi to get the area of this guy, right? So we have two different approaches here. So what do you want to start with first? So with that analysis, I know that the area can be given by 1/2, that's the mainstay, integral from 0 until pi over 3, because that's the first interval on which we are on the inner loop, right? And if you draw a ray here to know the area or to know the radius, from the pole, draw a line, and you see that the outer radius or the only radius will be on the limaçon. And the equation of the limaçon is 1 minus 2 cosine theta. So that goes in our integrand, 1 minus 2 cosine theta. It's in polar coordinates, so remember it should be squared d theta. But that is just the first half of the inner loop. So we need to add what's the area of the other half. But remember, we enter the loop again at theta equals 5 pi over 3. And then we will close it at theta equals 2 pi. So that means I will integrate from 5 pi over 3 until 2 pi to get the other half of the loop. Then the same integrand, because at that point, our dotted line will look like this. And the outer radius will still be the equation of the limaçon. All right. So this is one way of doing it, but remember we have spotted the symmetry here. So instead of this, you can just say it's 2 times either of these two guys. So probably let's just evaluate this and put that here. And this will give you the same answer, right? Because this guy is exactly the same as this one because they are symmetric, right? And that's one nice thing about polar curves, because they're usually symmetric to each other. All right. Okay, any questions so far? Any questions? Is this making sense? Okay. I hope it does. Okay, let's try another one. Let's see. Let's do equation example 3. Let's do the region outside r equals 2 plus 2 sine theta. But inside r equals 6 sine theta. Okay, so let's sketch the graphs. Let's start with this one, right? So we have a limaçon. The red, the one underlined with red is a limaçon, right? It's with a over b equals 2 over 2 equals 1. So we have a cardioid. So this would be a cardioid or a heart-shaped graph, right? So since I know the shape of the limaçon, I can just take a look at 5 theta values, which are exactly the quadrants. So theta equals 0, pi over 2, 3 pi over 2. Sorry, I need pi first, and then 3 pi over 2, and then 2 pi. All right. And then plug in this theta values into your r equation. Theta equals 0. This guy will be 0, so r is 2. Theta is pi over 2. This is going to be 1. So we'll get 4. Sine pi is 0, so we'll get a 2. 3 pi over 2, sine will be negative 1. 2 minus 2, so that's going to be a 0. And 2 pi, I'll just repeat what I got for 0. All right. Now let's sketch it here. All right. Now I need the 2 concentric circles to guide me plotting this radii. So let me draw r equals 2 here and r equals 4 maybe here. Okay. Now at theta equals 0, r is 2, so I'll have the first point here. When theta is pi over 2, so this is theta equals pi over 2, I'll put 4 units, so that would be on the larger circle. Okay, and then theta equals pi, so we're here, but we will have 2 units, so I'll be right here. Okay, and then we'll go this way, 3 pi over 2, we get 0. This is 3 pi over 2, we'll get 0. So we'll put it here. Okay, and then at 2 pi will be back at 2, right? So it's a heart-shaped graph or a heart-shaped limaçon or a cardioid, but remember that the limaçons are rounded graphs. So though it's a heart-shaped graph, it should be rounded. So it should look like this. Right. Something like this. Let me just try to enhance this if I can. Okay, so that's our limaçon or our cardioid, right? And then the other graph is a circle. Oh, by the way, here for the cardioid, it involves a sine, so we expected that it would be predominantly lying on the y-axis. So that's why it is going this way, right? If this was a cosine, then it would have gone this way, or something like that, right? So and also the coefficient of sine is positive, that's why it's pointing upward. If this was a -2, then it would have been pointing in that direction. So some ways to spot how limaçons look like, right? It's a sine, so predominantly on the y-axis. It has a positive coefficient, so it would be predominantly on the positive y-axis, right? Okay, then we have r equals 6 sine theta. So r equals 6 sine theta will be a circle tangent at the pole. So the pole is a point. And then since this is positive and you have a sine, So it will predominantly lie on the positive y-axis, and the diameter is 6. So it will look like this. Oops. Hold on, let me cheat here. Okay, there you go. Okay. So that's r equals yeah, that's r equals 6. So this is r equals 6 sine theta. And then the red one is, oops, let me not write there. It's r equals 2 plus 2 sine theta, right? Okay, now what's the shaded region? The shaded region is outside the limaçon, but inside the circle. So we'll have this region. More or less, right? So that's going to be our shaded region. Outside the limaçon, but inside the circle. All right. Now, what are the angular components? So maybe if it's confusing, maybe I can delete the concentric circles just to make the illustration much clearer. All right. Now, remember that the integral that will give us the area of the shaded region will have upper and lower limits equals the starting and the ending angles for the region. Well, the region will start here at this point of intersection, right? But we don't know what this angle alpha is. And then we will travel like a hand of a clock, but in the counterclockwise direction until the ending portion of the region, which will occur at the other point of intersection. So basically the angular span would be will be from this alpha value until the beta value. But fortunately, though we have an idea what those alpha and beta would be because they are the theta components at the points of intersection, right? The points at which the red curve and the blue curve intersect. Okay. Now let's solve for the theta values at the intersection. All right. And we do so by just equating the two r's. So look at this. The limaçon has r equals 2 plus 2 sine theta. The circle has r equals 6 sine theta. Both are equal to r, so we can make them equal to each other. So we have 2 plus 2 cosine theta. This is equal to r, but 6 sine theta is also equal to r. So let's put them equal to each other. All right. Now remember, for solving trig equations, we try to isolate the trig function to one side. So we'll have 2 equals, oh, sorry, it's not a cosine, but it was a sine, right? We subtract 2 sine theta from either side, so we'll have 4 sine theta. Okay, and so that means sine theta will be equal to 1/2. But when is sine theta equal to 1/2? Sine theta is equal to 1/2 at pi over 6 and 5 pi over 6. That tells us that this guy is actually pi over 6. And this one is actually 5 pi over 6. So that means the region, the shaded region, has an angular span from pi over 6 until 5 pi over 6, right? And so our integration will happen on that angular span. So the area will be the mainstay 1/2 times the integral. We know the exact theta values there. We're integrating with respect to theta, but what would be the integrand? To find the integrand, go to the region, draw a ray traversing the region, observe what is the inner and the outer radius. The outer radius is here. That's the ending portion of the region. The inner, which is the starting point of the region, is there, right? So it's going to be the blue. The blue curve is the outer. The red curve is the inner, right? Now, will that be true for the entire angular span? So imagine this line, this ray, being being rotated across the entire span. So remember, I started here, right? Imagine this starting from pi over 6. Look at it traveling across the region until pi over 6. But all throughout that experiment, the outer radius is always the red circle. Sorry, the blue curve, and the inner radius is always the red curve, right? So that means we don't need to split the integral up. There is a uniform behavior all throughout the angular span. So the outer radius is given by the blue curve, right? So it's going to be 6 sine theta quantity squared minus the inner radius, which is always the red curve, 2 plus 2 sine theta quantity squared, all multiplied by d theta. And there you go. That's going to be the area of the shaded region. Okay. Another approach is to take advantage of the symmetry. Because again, here, okay, you can simply integrate from pi over 6 until pi over 2. And just argue that it is symmetric with respect to the y-axis, right? Or to the theta equals pi over 2 ray. Because the area here, this area, okay, is exactly the same as this area over here. And this is the beauty of polar curves. Most polar curves, most common ones, are symmetric with respect to some rays or with respect to some lines. So it's easy to take advantage of the symmetry. So instead of doing the integration from pi over 6 to 5 pi over 6, I can simply integrate, okay, from 0 until pi over 2. Okay, so that will give me half of the shaded region, the area of half of the shaded region. So all I need to do is to multiply everything here by 2 to get the actual area of the entire region. So either way, you'll get the area of the region, okay? And that is fine. All right, any questions here? You guys are extremely quiet. I hope I made sense. But don't worry, on Friday, we can look at some more examples for finding areas for polar curves vis-a-vis looking at the detailed graph of the regions. Oh, there you go. Christina has a question. For loops, will they always touch the origin? For the basic polar curves that we will consider, yes, they will. They will always touch the origin or the pole. And the pole will be the starting and the ending point of the loop. Right, so if you want to get the starting point or the ending point of the loop, you can just equate the equation of the limason or the left-hand side of the limason, or the right-hand side of the limason to 0, or replace r equals 0. That will tell you when will you leave the inner loop. All right. So basically, r equals 0 for limasons with a loop will tell us when are you on the inside loop and when you are outside the inner loop. Okay. Okay, other questions? I hope that's fine. So let's see each other again on Friday and talk more about examples of finding areas of regions bounded by polar curves. All right, guys. Thank you for coming. Have a good day.